Welcome back to the Trilogy. In Part 1, we explored Rome's water empire, Egypt's stone precision, and the Indus Valley's quiet mastery of sanitation. Today, we're heading to three civilizations that turned landscape itself into an engineering material. Sub-Saharan Africa's Great Zimbabwe, the jungle metropolis of Angkor in Cambodia, and the mountain empire of the Inca. None of them used mortar, wheels, or iron tools the way we'd expect. And yet what they built has outlasted empires that had all three. What's striking about all three of today's civilizations is that their engineering wasn't just about individual monuments. It was about managing an entire environment, whether that meant taming a jungle's monsoon cycle, engineering earthquake resistance into a mountain city, or perfecting dry stone construction well enough to skip mortar altogether. Settle in. This is a deep one, and let's get into it. In the hills of what is now Zimbabwe, between roughly the 11th and 15th centuries, the Shona people built an extraordinary city now known as Great Zimbabwe. Its most famous feature is the Great Enclosure, a massive curved wall over 250 meters in circumference and up to 11 meters tall, built entirely from granite blocks stacked without any mortar. This is dry stone construction at its most advanced. Builders shaped granite blocks with such consistent dimensions that the wall has stood for over 600 years without a single binding agent holding it together. The stone was likely split from nearby granite outcrops using fire and water, heating the rock, then rapidly cooling it so it cracked along natural fault lines into workable slabs, a technique requiring precise timing to avoid shattering the stone unpredictably. Archaeologist Peter Garlake's detailed 20th century surveys identified distinct construction phases at the site, labeled P, Q, and R, showing that building techniques improved noticeably over generations. Early walls used smaller, less regular stones with more visible coursing gaps, while later phases like the Great Enclosure's outer wall show tightly coursed, carefully selected blocks with almost no visible gaps, evidence of a stoneworking tradition that was actively refining itself over roughly 300 years. The site is actually made up of several distinct architectural zones, not just the Great Enclosure. The hill complex, believed to be the earliest area settled, was built on a natural granite outcrop, and its walls weave directly around and between huge natural boulders, using the existing rock formations as structural anchors rather than clearing them away, a design choice that blurs the line between architecture and landscape. The valley complex housed the bulk of the population in a mix of stone walling and daga, a compacted clay and gravel material molded and dried in place, showing that Shona builders adapted their techniques to different purposes, budgets, and terrain, rather than applying one rigid method everywhere. Inside the Great Enclosure stands the conical tower, a solid, roughly 10-meter-tall stone structure with no known internal chamber or entrance, built using the same coursed stonework as the surrounding walls. Its exact purpose is still debated among archaeologists. Leading theories suggest it may have symbolized a grain bin, representing the ruler's control over the kingdom's food surplus and wealth, or served as a symbol of political and spiritual authority, since similar conical shapes appear in other Shona religious contexts. Excavations at the site also recovered soapstone carvings known as the Zimbabwe birds, mounted on tall monolithic columns which are believed to have represented ancestral spirits or royal authority and today appear on Zimbabwe's national flag. Great Zimbabwe was also the center of a trading network reaching as far as China and Arabia, evidenced by imported glass beads, Persian pottery, and Chinese Celadon porcelain fragments found at the site. Proof that this wasn't an isolated settlement but a connected hub of a continent-spanning trade route dealing in gold, ivory, and cattle. with gold likely sourced from smaller mining settlements scattered across the wider region and funneled through Great Zimbabwe toward Indian Ocean ports like Kilwa. At its height, the city is thought to have supported a population of around 18,000 people, making it one of the largest settlements in sub-Saharan Africa at the time. For a long time, colonial-era historians and officials invested in denying African peoples credit for sophisticated architecture, refused to believe Africans had built it, wrongly crediting outside civilizations like the Phoenicians or ancient Israelites. Modern archaeology, backed by radiocarbon dating and stylistic analysis matching regional pottery and building traditions, has thoroughly confirmed it as a Shona achievement, standing as one of sub-Saharan Africa's greatest engineering legacies. The city was gradually abandoned by the 15th century, likely due to a combination of factors including overgrazing of surrounding land, resource depletion, and shifting regional trade routes that favored other emerging Shona states. The very name Zimbabwe comes from the Shona phrase, Zimba Zamabwe, meaning houses of stone. And Great Zimbabwe wasn't a one-off achievement. It was the largest and most refined example of a wider dry stone building tradition. Related sites like Kami, which rose to prominence after Great Zimbabwe's decline, and Nalatela, known for its especially decorative chevron and herringbone stone patterning worked directly into the wall coursing, show that this construction knowledge continued spreading and evolving across the region for centuries afterward. Inside the great enclosure, a narrow curving passage runs between the outer wall and an inner parallel wall, too tight and indirect to serve any obvious defensive purpose, leading most archaeologists to interpret it as a controlled ceremonial route, guiding visitors on a deliberately choreographed path toward the conical tower rather than allowing direct access. Great Zimbabwe's builders were also skilled metalworkers, and excavations have recovered iron gongs, gold jewelry, copper ingots shaped for standardized trade, and evidence of on-site iron smelting furnaces, showing that stoneworking wasn't the city's only advanced craft. The combination of controlled cattle grazing, terraced hillside farming to manage soil erosion on the surrounding slopes, and this metalworking economy all supported a population far larger than the immediate stone city, spread across an estimated 700-hectare wider settlement zone, once fully mapped by aerial and ground survey. Deep in the Cambodian jungle lies Angkor, the capital of the Khmer Empire, and home to Angkor Wat. But the real engineering marvel isn't just the temple, it's the water system underneath the entire city. Between the 9th and 13th centuries, Khmer engineers built an enormous network of reservoirs called barays, canals and moats to manage water across a tropical landscape with brutal wet and dry seasons. The West Barai alone stretches roughly 8 kilometers long and 2 kilometers wide, dug and shaped almost entirely by hand, capable of holding tens of millions of cubic meters of water. Angkor Wat's own moat, nearly 200 meters wide and 5.5 kilometers around, wasn't just decorative or defensive. It also helped stabilize the water table beneath the temple's sandstone foundations, preventing the sandy ground from shifting or subsiding under the structure's enormous weight. Angkor Wat itself, built in the early 12th century under King Suryavarman II, used an estimated 5 to 10 million sandstone blocks quarried from the Kulin Hills roughly 40 kilometers away, floated down a purpose-built canal system on rafts, since no wheeled transport of the era could handle blocks of that scale across the region's soft, waterlogged terrain. The temple's central tower rises 65 meters and required builders to solve serious load distribution problems using corbelled arches, a technique where each stone layer projects slightly beyond the one below until they meet at the top, since the Khmer never developed the true keystone arch used by the Romans. The entire temple complex was also laid out with precise astronomical alignment, with certain passageways positioned so that sunlight strikes specific points during the spring and autumn equinoxes, showing that Khmer builders combined structural engineering with careful astronomical observation. Beyond Angkor Wat, King Jayavarman VII, who ruled from roughly 1181 to 1218 CE, launched one of the ancient world's most ambitious public infrastructure campaigns. Inscriptions at the Temple of Ta Prohm and elsewhere record that he commissioned 102 hospitals called Arogya Sala across the empire, each staffed with physicians, a dedicated chapel, and a documented supply list of medicines and staff rations. An extraordinary combination of medical and civil engineering coordinated at an empire-wide scale. He also built a network of roads radiating out from Angkor, dotted with rest houses called Dharmasala, spaced roughly a day's journey apart for travelers. Mirroring in function, though not in scale, the Roman cursus publicus we covered in Part 1. At the empire's ceremonial center, Angkor Thom, Jayavarman VII's walled city spans roughly 9 square kilometers, ringed by an 8-meter-high wall and a moat over 100 meters wide, with 5 monumental gates featuring towering stone faces and causeways lined with statues depicting a mythological tug-of-war between gods and demons churning an ocean of milk. A design that required precisely aligning dozens of massive individual stone figures along a single symmetrical causeway. At the city's heart, the Bayon Temple features 216 enormous, serene stone faces carved into its towers, requiring builders to carve complex, expressive imagery into blocks that also had to bear real structural load. This hydraulic network let Angkor support an urban population some researchers estimate reached up to 750,000 at its peak. By some measurements, the largest pre-industrial urban settlement on Earth, larger than any European city of the same era. LIDAR surveys conducted in the 2000s revealed the true scale of this achievement, exposing a sprawling grid of canals, roads, and rice terraces hidden beneath the jungle canopy that archaeologists had never fully mapped before, including a previously unknown mountain city called Mahendra Parvata. Archaeologist Bernard Philippe Grolier first proposed in the 1970s that Angkor functioned as a hydraulic city, where the entire urban plan revolved around water management for wet rice agriculture, a theory that LIDAR data has since strongly reinforced. Some researchers now believe overextension of this exact system, combined with climate shifts causing extreme droughts and floods documented in regional tree ring records, contributed to Angkor's eventual decline through the 14th and 15th centuries. Proof that even brilliant engineering has its limits when the environment itself starts working against it. Khmer engineers also built stone bridges using the same corbelled arch technique found in Angkor Wat's towers, applied horizontally to span rivers along the empire's road network. The Speen Praptos Bridge, for example, uses a series of corbelled stone arches to cross a river, and portions of it remained in active vehicle use well into the 20th century. A remarkable lifespan for infrastructure built roughly 900 years earlier. Maintaining the barrays and canal network was a constant, active engineering task rather than a one-time construction project, since tropical siltation from monsoon runoff steadily filled reservoirs with sediment over time, requiring ongoing dredging that historians believe became harder to sustain as the empire's political stability declined in its later centuries. Meaning the same water system that built Angkor's greatness may have quietly become a maintenance burden it could no longer keep up with. Beyond the Grand Berets, ordinary Khmer neighborhoods were laced with a dense secondary network of smaller household ponds and local canals, each connected to the wider system, letting individual temples and residential areas manage their own water supply and drainage, even during the driest months. Combined with an extensive network of raised earthen roads doubling as flood season causeways, this layered approach Massive reservoirs at the top, small local ponds at the neighborhood level, meant Angkor's water engineering worked at every scale simultaneously. From empire-wide agriculture down to a single household's rainy season drainage. High in the Andes Mountains, the Inca Empire pulled off something remarkable in the 15th and 16th centuries. An empire-spanning road network called the Chapak Ñan, stretching an estimated 40,000 kilometers, connecting present-day Ecuador, Peru, Bolivia, Chile, and Argentina, all without the use of wheeled vehicles or draft animals larger than a llama. The roads included suspension bridges made from woven grass fiber cables, some spanning canyons over 45 meters wide, rebuilt annually by local communities under a rotating labor system called the mit'a, where each community contributed a set amount of labor to the empire in place of taxes. The most famous of these, the Queswa-Chaka Bridge over the Apurimac River, is still rebuilt by hand every year by local Quechua communities using the same traditional technique, making it a living, functioning piece of Inca engineering rather than just a historical artifact. Along the road network, the Inca also built tambos, way stations spaced roughly a day's walk apart, stocked with food, supplies, and lodging, supporting both traveling officials and the empire's messenger system. Teams of trained runners called chaskis who relayed messages in a continuous relay, reportedly capable of carrying news up to 240 kilometers in a single day across the mountainous terrain. At Sacsayhuaman, overlooking Cusco, Inca builders constructed massive polygonal stone walls from blocks weighing over 100 tons each, cut and fitted so precisely that no mortar was needed. And the interlocking, irregular shapes have helped these walls survive earthquakes better than many modern structures, since the stones can shift slightly and resettle rather than cracking under seismic stress. The walls are also built in a distinctive zigzag pattern across 3 parallel tiers, a design that may have served both defensive purposes, creating angled kill zones for defenders, and symbolic ones, since Inca oral tradition described the fortress's outline as resembling the teeth of a puma, with Cusco itself said to be laid out in the shape of the animal. Researchers still aren't entirely certain how the Inca achieved such tight-fitting joints on stones of that size, though evidence points to repeated test-fitting grinding surfaces with sand and water, and possibly bronze tools for finer shaping. Inca engineers also had a deep understanding of foundations and earthquake resistance more broadly. At Machu Picchu, built around 1450 CE as a royal estate, walls in the most important ceremonial buildings use ashlar masonry, precisely cut, interlocking stone blocks fitted without mortar, while less critical structures used a rougher fieldstone style, showing builders deliberately matched construction quality to a building's importance. Many of Machu Picchu's walls also lean slightly inward, a technique called batter, which modern structural engineers studying the site believe helps distribute seismic energy and resist earthquake damage, a design principle later validated by shake table testing on scale models. Beneath the surface, the city's terraces conceal a multi-layered drainage system of soil, sand, and gravel, engineered to prevent the mountainside from eroding or flooding during the region's intense rainy season, which can otherwise trigger dangerous landslides on such steep terrain. The Inca also developed extraordinary agricultural terracing at sites like Moray, where circular terraces created distinct microclimates at different depths, with temperature differences of up to 15 degrees Celsius between the top and bottom levels, letting them experiment with growing crops at a range of simulated altitudes and temperatures in one location. An early form of agricultural engineering and climate testing rolled into one. At Tipon, another royal agricultural site near Cusco, engineers built a system of stone-lined canals, fountains, and terraces fed by a natural spring, using precisely calculated channel gradients to distribute water evenly across multiple terrace levels simultaneously. A design so effective that some of its canals still carry flowing water today, over 500 years after construction. At Ollantaytambo, a partially finished Inca site in the Sacred Valley, massive stone blocks weighing up to 50 tons still sit abandoned on the slope leading up from the quarry, along with a purpose-built ramp system used to move them, giving historians a rare, unfinished window into exactly how Inca crews transported enormous stones across valleys and uphill without wheels. Relying on a combination of log rollers, earthen ramps, and sheer coordinated manpower guided by respected foremen, the Inca state also built and managed a vast empire-wide network of storage warehouses called kulka, typically constructed in rows on cool, well-ventilated hillsides near major cities and road junctions. Engineered with raised floors and strategic airflow to preserve dried food, textiles, and other goods for years at a time. Combined with the road network and the knotted cord record-keeping system known as the quipu, which administrators use to track inventories, census data, and labor obligations. This storage system let the Inca state respond to famine, supply military campaigns, and redistribute resources across a mountainous empire spanning nearly the entire length of South America's western coast. Logistics engineering every bit as impressive as the empire's stonework. Cusco itself, the Inca capital, sat at the convergence of two rivers, the Saifi and the Tulumayo, which Inca engineers channeled into stone-lined canals running directly beneath the city streets to control flooding and provide clean water access, with sections of that same channeled stonework still forming part of the city's drainage infrastructure today. And on the steep slopes surrounding the Sacred Valley, terracing at sites like Pisac shows Inca agricultural engineers routinely carving farmland directly into cliff faces, at gradients that would be considered extreme even by modern standards, using retaining walls angled specifically to withstand the pressure of saturated soil during the rainy season without collapsing outward. A problem modern civil engineers still study when designing hillside retaining structures today. That's part 2. Dry stone mastery and continent-spanning trade in Zimbabwe. Empire-scale hydraulic engineering and public health infrastructure in the Cambodian jungle, and earthquake-resistant, mortar-free stonework high in the Andes. In our final part, we're heading to China and the Islamic Golden Age to see how engineering ideas traveled and evolved across an entire continent. Thanks for watching. If you're enjoying the series, leave a like and subscribe so you catch part 3.